Hi. Today we're going to start a new unit. We're going to start talking about this thing called gas laws. And to get started, as usual, jot down any questions you have, any neat observations you make as you are watching this video. Oh, that kind of works perfectly. They just asked the question I had. Why is it that it doesn't pop when there's many nails, when it does pop when there's one nail? You'd think with like 100 nails, it would pop all that much easier. Any one of them would be able to pop it. So to build up this idea, I wanted to define pressure for everyone. So the formula is there. Pressure is force over area. And we're going to define a force as any push or a pull. That might be a little vague or broad of a definition, but just go with me on it. That is the simplest way I can define a force. And then area is, of course, any two-dimensional space, length times width, or any other two things that you're multiplying. Based on this formula, we can come up with some relationships between these three factors, variables: pressure, force, and area. Whenever you have two things on opposite sides of an equal sign, that gives you a direct relationship. As force increases, pressure increases. So high force is high pressure, and low force is low pressure. And then we can see when you have that equal sign, but it's a fraction. If it's a denominator and a numerator that you're relating, they're inversely related. As area increases, pressure decreases, or pressure varies directly with 1 over area. That is to say, as area goes up, 1 over area goes down. So this would lead to a decrease in pressure. And so that's where we get our relationship, our direct relationship. They both go down together. So it seems like there's sometimes when you have things on one side of an equal sign, it works out that they vary directly, and sometimes they vary inversely if there's a fraction involved. This image I got here might help also explain what's going on. This shows one of the two variables. We have the same person, the same hammer, the same wall. The difference is what we're hammering in is either a bowling pin or a nail. And the difference here is the bowling pin is making contact with a much larger area than the nail. The nail has a very, the tip of a nail is a very small area. And so if you have the same force, the same hit, but you're dividing by a smaller number, well, a big number divided by a small number is even bigger. If you want some numbers to put it to, that would be like saying if we have the same one force and the area of the bowling pin is, say, 10 versus 1 over 2, right? So mathematically, this is 0.1 and this is 0.5. So you can see as the 10 goes down, the quotient goes up. So how does this relate back to gases, right? Like, that's great that that's pressure, but what we saw in the video was a balloon, and I also I'm not 100% sure whether it's the balloon's pressure I should be worried about, or if it's the nails pressure. Like, there was a lot of the hand was pushing, but did the balloon push? And the short answer is yes. Whenever you have a balloon, as that balloon was blown up, it expands. What that situation is when you tied off the balloon, what that situation is the gas on the inside of the balloon and the gas on the outside of the balloon are both pushing on that fabric of that balloon. I think what we have here is a situation of a person drawn in a garbage bag. If you've never done this, this is a fun game to play. Like, you put a leaf blower inside the bag and it blows up the bag really big, and it's fun. But yes, how these particles are moving. We talked about a gas before being this substance that has an indefinite volume because the particles are very spread out, but also we have this thing called temperature or kinetic energy. So all particles have temperature, and that kinetic energy will then yield a force as the particles hit the side of the container. You'll see force from these gas particles on both sides of the container, and that's why the container stays the same size. Now, of course, I'm talking about something that is stretchy, like the rubber or latex of a balloon. If the substance that you have the gas in is rigid, say like a sealed can of soda or something, that's different. Like it's not changing in size. There can still be force, but that's a little bit more complex. A balloon has to be a certain size. If the balloon is not changing in size, we have two forces. And what we can say is the force on the inside equals the force on the outside. And if that's the case, well, if the area is the area, right, it's the same balloon, the same area on the inside and the outside. So if we divide both by the same area, what we get is the pressure on the inside equals the pressure on the outside. And you can get that size, that pressure to change, right? Like you can get more force or less area. We can see that happening. And that's what happened in the video. When you have one nail and a balloon, that's a very small area like we saw before. But if we have several nails and the same balloon, forgive my lack of scale with drawing, each of these is now pushing on a small area relatively, right? This piece of nail can only really push on that one tiny part. They're all pushing, but they all kind of push together, and so they don't concentrate into one little area. Now, you can get the size to change because of area changing or because of force. If the force on the inside is greater than the force on the outside, then that would mean that the pressure on the inside is greater than the pressure on the outside. And we said a force is a push or a pull. If the pressure on the inside is greater, then the balloon will push outward. Now, when the balloon pushes outward, that changes the area. Hopefully you can see here, these two bags they look like they have different areas. This one is a low area, and this one's a high area. If the pressure inside is high, then that will push that area out. But remember, we said that pressure is force over area. If the area goes up, then the pressure would go down on the inside, that as it stretches. And so eventually what we'll end up seeing is some later time, as the size increases, the pressures would then be equal to each other again. And that's when the balloon stops expanding. So if you've seen something, like you've seen this, when you blow up a balloon, you take a breath, you blow it out, and when you blow in, the balloon gets bigger, but then eventually it stops getting bigger. Probably because you stopped putting air into it, but the amount of air in it is causing that force to be higher, the pressure's higher, and then the balloon expands. So all the while we're dancing around this idea of force, area, and pressure, and I did want to mention one other thing. So now that we've established this idea of air pressure, you're under pressure right now. So am I. Above my head, there's a whole atmosphere of air. This planet is surrounded by a layer of air, and all that air is being pulled down by gravity, and as it's pulled down towards the surface, it pushes on things that are on the surface, like you. And if you want to see the effect of air pressure, it's real easy. You may have even done this before. If you get a piece of paper or a piece of plastic, you get a cup, and you fill it with water, and you put the piece of plastic just over the top, and then you turn it upside down, you can take your hand away, and the piece of plastic won't fall. And that's because there's air all around this piece of plastic, and it's pushing up, but there's no air here to push down. There's that cup of water in the way, so it's blocking all that air. And so if the push up is greater than the push down, then that's what's holding that piece of paper there. Of course, if you tap the side of the paper, the water comes out, air can get in, suddenly there's air pressure on both sides, and the plate falls because then there's also gravity, right? Gravity's not being shown there. This simple design of a cup being upside down and holding a piece of paper or plastic up is the science on which a barometer is made. And this is a barometer right here. You take a glass tube, much like a cup, and you fill it with mercury. And then you put your thumb over the top. Don't actually do this. Mercury's dangerous. And then you put it in a dish, and you take your thumb off, and the mercury will start to drain. Now, if you were careful about filling your tube, and there's no air in the tube whatsoever, even though the mercury's draining, there's nothing above it. And so what we have here is a vacuum. We're going to define a vacuum as no matter present. So in this little space here, there's no matter. which means that there's air pushing down. This basin is, of course, open, and then there's no push here. The only push we have is the air pushing down on the mercury, and then, of course, there's gravity pulling down on the mercury, too. So we're balancing out that gravity versus the push of air. And it turns out, first off, these barometers were first made by a man named Torricelli, that the amount of mercury that gets pushed up is variable to the air pressure. As the pressure goes up, there's more push down, and the mercury will go up, and the distance that the mercury goes up will increase. And then as pressure decreases, if we have lower pressure, then there's less pushing, and then the mercury will sink. So the height of that mercury column can be directly related. That's what we report when you're watching the news and they say the barometer is rising and it's 30.31. What they mean to say is it's 30.31 inches. The amount of mercury that can be suspended by atmosphere on average is about 760 millimeters, or 29.92 inches, about 30 inches. So like if you can picture a yardstick. Now, if we used a different substance, like say water or any other liquid, you might get a different number because it's a different substance, different properties. You don't want to use water though, because water evaporates. And so that's going to muck up with this. Mercury as a substance has a very, very low evaporation rate, almost zero, which is why we use it for barometers. But this also leads to a different discussion, because now we've seen these two units right next to each other, and obviously it's easy enough to convert between millimeters and inches. But also, if you look on your reference table under Table A, labeled Standard Temperature and Pressure, also known as STP, anytime I say that moving forward. Of course, don't forget, link to the reference table above my head. You'll see other units, these kPa, kilopascals, or atmospheres. So let me write out what these are really quick. We see only two of them here, right? 101.3 kPa and 1 atmosphere. Those represent the same pressure. And we call that standard pressure because obviously with weather, pressure changes. And so, we're willing to say as a scientific community, this is the pressure that we're going to use. We're going to call it normal pressure. You can also see standard temperature right below it, which is rather cold. I mean, it's about 0 Celsius outside right now, but, We have those two, and then I also wanted to relate back. So this 1 ATM, atmospheres, because we're all on Earth, and because all of human history has taken place on Earth, and all of science, other than the moon, is on Earth, the pressure that we see here we call 1 atmosphere. What you're feeling now is about 1 atmosphere of pressure. Don't worry, all those little gas particles hitting you in the head, you felt it your whole life. So that's why it doesn't really feel new or feel like you're being pushed on just by the air. I guess it could feel like that. We have these other two measurements here, 760 millimeters. This is, we don't really use inches, right, in chemistry, but you'll see that on the news, which is why I mentioned it. This millimeters of mercury got a name, additionally, in addition to millimeters of mercury, it got a name of Tor, after Torricelli, the man who did a lot of the work for those early barometers. So what we have here now are 4 measurements: 101.3 kilopascals, 1 atmosphere, 760 millimeters of mercury, and 760 torr. All 4 of these measurements represent the same amount. So just like we've had before, where we have 2 different ways to represent the same measurement, these represent potential conversion factors, where given how you're getting your data in, you can convert it to a different usable unit. So just to practice that really quick as a brief reminder of how this works, we're going to translate both of these into kilopascals. We've got this information here. I'll also give you that number again, 760 torr. So I can't remember if it's capital or lowercase. I guess I should fix that down here. I can't 100% remember. Now, yeah, I should check it later. If you need help with your dimensional analysis, we can do the first one together, but if not, you can pause the video, do this yourself. We start by writing our given quantity. Our canceling unit is going to go in our denominator. We're asking 2 kilopascals, so that's going to go in our numerator. The numbers are right here on table A. We know 101.3 kilopascals for every 1 atmosphere, and so multiplying across, you get about 76 kilopascals. The atmospheres cancel. It's like 75.97, so we're going to round that to the nearest whole number to match up our significant figures. And then again, so if you want to do this yourself, go ahead. In this case, it might be a little bit harder to figure out, right? We've got our 760 torr. We're going to have to use that number. But then our top number is 101.3. I think this is the first time, other than like our mole-to-mole stoichiometry, where this is you don't have any ones in our conversion factor. If you want, you could write this as two separate steps, where you go from torr to atmospheres and then atmospheres to kilopascals, whatever you think is easiest. So we're going to do our dividing, multiplying, and what we get out of here is 61.3 kilopascals. Maybe you want to drop that 0.3 and just call it 61. The idea there is, this feels right? 460 is a little more than half of 760, so it would make sense that we have a little bit more than half 101.3. Thanks for watching.